Welcome back, Chemistry 30. This is the EC1.6 Spontaneity of Redox reactions. So we kind of touched on this already, and this final section just kind of continues on with that. So predict the electric potential and spontaneity of various redox reactions using their reduction potentials. So we have observed that voltaic cells, or electrochemical cells, use spontaneous redox reactions to produce a positive cell potential. We can use this fact together with half-life potentials to decide whether it is spontaneous or not. So of course we use this idea from before. If we make it more general though, so it doesn't have to be an electrochemical cell, it could just be a redox reaction, we could change it to, well, at the cathode, that's where reduction happened, and at the anode, that's where oxidation happened, losing electrons. Instead of electrochemical cell, we could just simply call it voltage, or just E, just in general. So in writing the equation this way, we have dropped the subscript cell to indicate that the calculated EMF, or electromotive force, or voltage, does not necessarily have to be from an electrochemical cell. Also, we generalize the standard reduction potentials by using the general terms reduction and oxidation rather than cathode and anode. We can now make a general statement about the spontaneity of a reaction and its associated EMF. So of course we mentioned that a positive value of E overall represents that it is spontaneous. A negative value indicates that that will not happen spontaneously. So it's just like what we did before with a couple of different questions for this part. We use E to represent the EMF under non-standard conditions, and E with the raised subscript E naught to indicate the standard EMF. So here we'll use Appendix E, so this sheet right here, the standard reduction potentials to determine whether or not the following reactions are spontaneous or not. So here we have a reaction here involving copper and the hydrogen cell, and here we have chlorine and iodine. Now on the next page, I believe, there's a lot of room, so what we can do is work that there. Or maybe what we'll do is we'll work A over on this page, and we'll look at B on the next one. Okay, so over here, if we look over here, so here we have our reaction, and according to this reaction, copper is going from solid copper to copper 2 plus. So of course that is going to be losing electrons, so they're assuming that this is the anode. So the anode will be copper going to copper 2 plus, and of course in the process we'll be losing electrons. So if I look over here for copper and copper 2 plus, look up the reduction part of that. So copper 2 plus going to, solid, or no, it is solid copper. So I'd have to look at it reverse, right? Copper 2 plus going to copper solid. Copper 2 plus, where was it? Copper 2 plus, there it is, going to copper solid. So you have to be careful because there's two copper 2 pluses there. Going to solid copper plus 0.337. So E, and then plus 2 electrons. And the E there, the E, and we'll just simply call it E reduction. It's going to be, what did I say there? Plus 0.337. Hopefully we can see that on the screen. It's a little bit cut off. Okay, and we're assuming that hydrogen ions gain electrons to make hydrogen molecules. So when we're gaining electrons or taking them in, that's of course the cathode. So it's assuming here that hydrogen ions are making hydrogen molecules. So of course if we look over there, hydrogen ions, let's see if we can actually see that. Hydrogen ions to make hydrogen molecules, and of course that is 0. 2 H's plus 2 electrons. 2 H's plus 2 electrons give us our H2. And of course that's going to give us 0. So when we set that up, so according to the equation, they have the equation set up, we have to see, is this equation actually going to work? So E, now we're dropping the E cell, so E standard, and E, the reduction potential, when we're talking about the reduction part of the equation, minus the reduction potential at the oxidation area. And of course we had this, maybe I shouldn't have, so at the anode, of course, that's where we have oxidation. Maybe instead of talking about the anode and cathode, I should have talked about oxidation and reduction. All right, so reduction will be 0. Okay, and we can see there's going to be an issue here, isn't there? Minus at the oxidation, which would be the anode if it was an electrochemical cell, plus 0.337 volts. And of course, negative and positive, we get a negative value here. All right, and we could have seen that too, actually, because remember, wherever we have, if it's a cathode and anode reaction, electrochemical cell, we know that the cathode, or where the reduction happens, must be more positive than where I have oxidation or the anode. So since E naught is negative, the reaction is non-spontaneous. So it's non-spontaneous. So maybe pause the video and see if you can do B. So very similar setup. Do it on the next page though, because there's more room there. And you can label it anode and cathode like I did, or just put anode where oxidation is and reduction. So I think I'm just going to use the terms oxidation and reduction, since we're using a more general form of this formula to represent oxidation reduction, not necessarily an electrochemical cell. Okay, so I'm going to pause the video and try that question out. All right, so hopefully you had a chance to do that. I took the liberty of writing out the equation here. So let's see here. Let's look at where the oxidation would be. Oxidation, so of course that's where the anode would be. And of course reduction, that's where the cathode would be. Now, so let's take a look. So here we have Cl, neutral, going to Cl minus, so we know that's going to be the reduction part. Cl. Cl2 going to Cl minus. And of course it's 2. Let's look this up. Cl2, chlorine going into chlorine ion. Chlorine, right here it is right here. So chlorine gas going to the chloride ion. So it's plus 2 electrons, plus 1.359. Plus, what did I say that was? 1.359 volts. And that means the other one must be the anode. So I'm going from I here is -1, going to 0 with the oxidation number. So obviously that's being oxidized. So iodine, the iodide ion, is going to iodine, and that should be 2 electrons. Let's look that up just for kicks. And of course, on the reduction table, it's reversed. It's showing iodine. Let's see if we can find it. There it is right there. So iodine plus 2 electrons gives us 2 iodides, and that value is plus 0.536. Plus 0.536, and we could actually do a check right here to see if this is going to work, because the cathode, or where the reduction happens, must be more positive than the oxidation area or the anode, and yes it is. So this one will work. So we still need to show it though, because the question wanted us to. And so where we have reduction minus the reduction potential of where we have oxidation, plus 1.359 volts minus plus 0.536 volts. minus positive. So that's going to give us plus 0.823 volts. Therefore, since E naught is positive, the reaction is spontaneous. So that will be spontaneous because we get a positive value there. All right. So hey, we're going to do the same thing with the next 3 examples. Maybe pause the video. So before I do the next video, maybe try these. And then in the next video, the last video, I'll go through each of these and we'll see how you did. All right, we'll see you soon.